Instead of A dot B, I'll write it as A dot A. It will be AA cos 0 because the angle will be 0. So the dot product of two equal vectors will be A square. Once the vectors are acting in opposite directions, the angle will be 180 degree. What is cos 180? It is minus 1. dk by dt is dt into half mv square. We know that half mv square is nothing but the kinetic energy. The gravitational force is acting downwards, whereas the lifting force is acting upwards. Hello students, welcome to this first session on chapter 5 on work, energy and power. I am Madhu R from the Department of Physics at Vidhyaashram PU College, Mysuru, your temple of excellence. To better understand the concept of work, which we will see that is a product of force and displacement, we need to understand what is the scalar product of vectors. Okay, we need this mathematical entities called as vectors and especially the scalar product of vectors. So what is this scalar product, which is also called as a dot product, because it is represented as vector A dot vector B, vector A into vector B. This is called as a dot product. It is defined as the product of magnitude of the first vector and the component of the second vector in the direction of the first vector. What does that mean? Let us have a look at this sketch. There are two vectors, vector A and vector B, acting at an angle theta with each other. So what is the dot product of these two vectors? It is the magnitude of vector A and the component of vector B in the direction of vector A. Component of vector B in the direction of vector A is B cos theta. Okay, so A dot B will be AB cos theta, where theta is the angle between the two vectors. Okay, so to better understand the concept of work, we need to understand all the properties of a scalar product of two vectors. Let us check them one by one. The first one, dot product is commutative in nature. What does that mean? A dot B is equal to B dot A vectorially. Okay, so we know that A dot B is AB cos theta. Similarly, if I take B dot A, it would be BA cos theta, nothing but AB cos theta. So A dot B is equal to B dot A for any two vectors. Now let us check one more property. Dot product is distributive over the addition of vectors. Okay, what does that mean? A dot of B plus C should be equal to A dot B plus A dot C. So small proof once again. I will take this B plus C as one entity or a single vector. So if I have the dot product, it will be A into B plus C cos theta. So if I open the brackets, it will be AB cos theta plus AC cos theta. Go back to vector product of two vectors, dot product. So what will that be? Dot product of two vectors is AB cos theta. So I can write AB cos theta as A dot B and AC cos theta as A dot C. So A dot of B plus C will be A dot B plus A dot C. This is distributive over the addition of vectors. Let us check further. What will happen if I have the dot product of two parallel vectors? Suppose I have one vector, vector A, and I have got one more vector, vector B, which are parallel to each other. Please remember, the magnitude of parallel vectors need not be the same. If it is same, then it will become equal vectors. Okay. What is the angle between two parallel vectors? So, theta is 0 degree. If theta is 0 degree, cos theta is cos 0, which is 1. Okay. So A dot B will be AB. Now let us check the case of two equal vectors. There are two vectors which are equal to each other. That is, the magnitude and the direction are same. Okay. So instead of A dot B, I'll write it as A dot A. It will be AA cos 0 because the angle will be 0. So the dot product of two equal vectors will be A square. Now, if I take unit vectors along x, y and z axis, I cap into I cap will be 1. Similarly, j cap into j cap will be 1. K cap into k cap will be 1. Okay. So whenever there are equal vectors you can see that the components of unit vectors along x, y and z axis will be 1. Let us check what will happen to the dot product of perpendicular vectors. Perpendicular vectors implies that theta is 90 degree. So what will happen? A dot B is AB cos 90. Please remember cos 90 is 0. So the dot product of two perpendicular vectors shall be 0. Similarly, if I multiply I dot into J dot or J dot K, K dot I, the answers that I get will be 0. Okay. You can also check the dot product of two anti-parallel vectors or opposite vectors. I have two vectors which are acting in opposite directions. Once the vectors are acting in opposite directions, the angle will be 180 degree. What is cos 180? It is -1. So A dot B for two vectors, if they are acting in opposite directions, their scalar product or dot product shall be -AB. Okay. These are few of the properties. Now let us check what is the dot product of two vectors in terms of their components. In terms of their components in x-axis, y-axis as well as z-axis. Okay. Let A be ax I cap, ay j cap, az k cap. Similarly, B be bx I cap, by j cap, bz k cap. What will be the dot product? A dot B I will get, please remember, it's a 3 cross 3. So I will get 9 terminologies. Ax I cap, ay j cap, az k cap into bx I cap, by j cap, bz k cap. I am first taking ax I cap. So ax bx I dot I, ax by I dot j, ax bz I dot k. Okay. Next, if I take ayj, okay, ay bx j dot I, ay by j dot j, ay bz j dot k. If I take the third term, az k cap, az into bx k dot I, az into by k dot j, az into bz k dot k. Now please check here, out of the 9 terminologies, only 3 terms have I cap, j cap and k cap. In the previous slides we have checked that for parallel vectors, I cap into I cap, j cap into j cap, k cap into k cap, the value is 1. For all the others, I dot j, I dot k, j dot I, j dot k, k dot I, k dot j, they all turn up to be 0. So I'll have only 3 terminologies left, which is the dot product of two vectors. Vector A dot vector B is ax bx, ay by and az bz. Okay. Now let us check what is the angle between two vectors. Let theta be the angle between the two vectors, vector A and vector B. A dot B we know is AB cos theta. So what do I get? Cross multiplying cos theta is A dot B by magnitude of vector A into magnitude of vector B. We have already seen what is the product of A and B. It is ax bx, ay by and az bz. Magnitude of vector A is square root of ax square plus ay square plus az square. Magnitude of vector B is square root of bx square plus by square plus bz square. Okay. So this will be, theta will be cos inverse of this product. Is that understandable? We will require these while solving the numericals. Now let us come into the topic. We said that this chapter is named work, energy and power. Let us check what is work first. Work is said to be done when a force applied on a body. Okay. If I push a table, the force is the pushing force. What is the body? The body is the table. When a force applied on a body displaces the body through a certain distance in the direction of the applied force. I push a table, the table is pushed by some distance. Okay. The unit of work is joule. Okay. How to define 1 joule? Consider that W equals Fx cos theta. if force is 1 Newton, the displacement of the object is by 1 meter, and theta is 0 degree, which means that the body is displaced in the direction of the force, then work is said to be done by 1 joule or 1 Newton meter. So 1 joule of work is said to be done when a force of 1 Newton is applied and the body is displaced by 1 meter in the direction of application of the force. Okay. Let us move ahead and check. We have already said that work is force into displacement into cos theta if at all there is any inclination, where F is the force acting, X is the displacement, theta is the angle between the direction of F and X. Okay. What are the special cases here? If theta equals 0, cos 0 is 1. Okay. If the body is displaced in the direction of application of force, then work done is maximum. Suppose theta is 90 degree. I am trying to push it, the object gets lifted. Okay. So the force and displacement are perpendicular to each other. What happens? Cos 90 is 0. Work done will be minimum. Okay. Work done is always the dot product of force and displacement. So work done is F dot X or Fx cos theta. Please remember that the nature of work done can be 0, positive or negative. It can happen in all 3 ways. Let us check how it can happen. 0 work. Please check the relation. Work is equal to Fx cos theta. If by any case the force applied and the direction of displacement is 90 degree, if theta is 90 degree, then work done is 0 because cos 90 equals 0. What is the example for this? You lift a bag or an object on your head and keep walking. The load is in the vertical direction, but the displacement is in the horizontal direction. So that can be a typical example of 0 work done. Okay. Work done is 0 when force and displacement are perpendicular to each other. Let us check when positive work is done. The force and displacement are in the same direction. I apply a force on the table, try to push it, the table moves away. Okay. So the application of force and the displacement is in the same direction. It means that whenever theta is less than 90 degree, work done is positive. Maximum work is done when theta is 0. Up to 90 degree, it remains positive. Okay. When is negative work done? The force and displacement are in opposite directions to each other. That is, theta is greater than 90 up to 180 degree. Whenever you are doing a work, that work is said to be negative in nature. Typical application or example, application of brake. The vehicle is moving in the forward direction. The brake tries to stop the vehicle or it acts in the opposite direction. It is typically negative work. The work done by the brake on the vehicle is negative in nature. Now let us check work done by a constant force. The graphical representation of work done by a constant force can be seen here. Okay. There is a displacement along the x-axis. The force remains constant. Okay. The above graph shows that force F is constant with increasing displacement x. The work done by force is typically given by area under the displacement curve. So whatever is the area under the displacement curve, this will let me know what is the work done. So work done is OA into OC, or typically work done is force into displacement, F into X. Okay. Let us come to a very important concept called as work energy theorem. The work done by the net force in displacing a body is equal to the change in kinetic energy of the body. So work done is equal to change in kinetic energy. Whatever the kinetic energy was initially there, difference between initial and final kinetic energy. There is some change in kinetic energy. Whatever is the change in kinetic energy, that will be equal to the amount of work done. This is what the work energy theorem states. Okay. In the figure, let u be the initial velocity of the body before some force is applied. Okay, v be the final velocity of the body after the application of force. Let that force be F. Okay, let x be the displacement from initial position to final position. Let m be the mass and a be the uniform acceleration of the body. Let m be the mass and a be the uniform acceleration. We already know that the kinematic equation says as v square plus u square equals 2ax, or v square minus u square equals 2 into a into x. Multiplying both sides by half m or m by 2, what do we get? Half mv square minus half mu square. I have taken half m common, v square minus u square equals half m into 2ax. Please note this half gets cancelled. I'll open up the bracket. Half m square minus half mu square equals max. Please check that force is given by mass into acceleration. So let me replace ma by f. Okay, this is half mv square, which is nothing but the final kinetic energy. Half mu square is nothing but the initial kinetic energy, or the change in kinetic energy delta Ke is equal to F into x. What is F into x? We know that force into displacement is nothing but the work done. So change in kinetic energy is equal to the work done. This is nothing but the work energy theorem. Okay, we have checked how work done behaves along with a constant force. Now let us check work done by a variable force. What do you mean by a variable force? The force keeps on changing as the displacement happens. Okay, the figure shows the variation of force F acting on the body with its position at x. In this case, the force is not constant from P to Q. Okay, from P to Q, the force is not constant, it is changing. There is a variation in the force. Therefore, the region below this curve will give us what is the work done. We already know. But how do I calculate that area? It is not a standard geometrical figure. What have I done? I have divided it vertically into a number of rectangle-like figures. Okay, let me take one of them. I have named this rectangle as ABCD. Okay, I have divided the entire sketch into a number of small rectangles like ABCD, each having a width of dx. Okay, so there is a small change in width, or there is a small change in displacement. That is why I have given the term dx. Through this small displacement dx, F is a constant. You can see that for this distance dx, the force remains constant. Okay, work done during displacement dx is given by, for this displacement dx, work done is given by the area under that part of the curve. How do I do it? It is AC into CD. Small work done dW is given by AC into CD, or F into dx. Force into small change in displacement. Total work done for this entire area can be obtained by summing up the area of all these small rectangles, or mathematically I can integrate the area of all these rectangles. How do I do? Work done by integration from point x1 to x2, all those rectangles which have dW as the work done. We already know that dW is F into dx. So I will substitute for work done integral x1 to x2 f of x dx. I have used the terminology f of x because the displacement is x. Okay, where f is the function of x. Work energy theorem for a variable force, we know that K is equal to half mv square. Differentiating both sides with respect to t, dk by dt is dt into half mv square. We know that half mv square is nothing but the kinetic energy. Differentiating, I have half m is constant, I have taken it out. D by dt of v square is 2v into dv by dt. Okay, this 2 and this 2 gets cancelled. M into dv by dt into v. What is variation of velocity with respect to time? It is acceleration. Acceleration is rate of change of velocity with the time. So instead of dV by dt, I'll write it as m into a into v. So dk by dt, ma is nothing but force. Force is equal to mass into acceleration. So instead of ma, I will write it as fv. Okay, dk by dt is f into v, but also I can write this v velocity as a rate of change of position by time, dx by dt. So this is f into dx by dt. What do I have? I know that initial position is xi, final position is xf. Initial energy is ki, final energy is kf. So integrating energy from ki to kf and integrating the position from xi to xf. What do I have? F dx from xi to xf, ki to kf dk integral. So I have work done. F into dx is force into displacement. When I integrate, I get work done. And I have change in energy from ki to kf. So work done is difference between the final and the initial kinetic energies. So this is nothing but work done by a variable force. Change in kinetic energy shall be the work done. That is the essence of it. Now let us check what is energy. We have had some information on what is work done. Energy is the capability to do work. What is the types of energy? There are many types of energy. We will come to that later. Let us start our study from a mechanical energy. What is mechanical energy? It is the energy possessed by the body by virtue of which, what? By virtue of motion, by virtue of position, or by virtue of configuration. Okay? So it is the energy possessed by a body by virtue of its motion, by virtue of its position, or by virtue of its configuration. Let us understand that in detail. Mechanical energy can be classified into two types: kinetic energy and potential energy. What is kinetic energy? Kinetic energy is the energy possessed by the body by virtue of its motion. Because there is some motion in the body, there is some energy in the body. That energy is called as kinetic energy. Similarly, what is potential energy? It is the energy possessed by the body by virtue of its position. Okay? Based on the position of the object, it may have some energy stored in it. A stone is lying on the floor, does not have any energy. A stone is lying on the first floor, it drops on your head, it can cause some damage. Because of the position in which that object is, it carries some amount of energy. Okay? Now what are the types of potential energy? There are basically three types: the gravitational potential energy, elastic, and electrostatic. For our study, it is more focused on the gravitational potential energy. Let us check what is gravitational potential energy. It is the energy possessed by the body by virtue of its position. Because we are saying that it is gravitational, we say that that position is above the Earth's surface. If it is on the surface or above the Earth's surface, then that potential energy is called as gravitational potential energy. What are the examples? A stone placed on the roof of the house. I gave you this example. Water stored in the overhead tank. It will possess some potential energy. That is why inside your house, if you just turn on the tap, the water comes down. Because the water stored in the overhead tank will have some potential energy. Now, let us understand this potential energy more. Consider a block of mass m. Okay? See, there is a block of mass m which is to be raised by a height h above the ground. So this block is on the floor, it has to be raised by a height h. Okay? What is the work done by the external force? Work done is force into displacement. Okay? Force into what is the displacement? It is height h into cos theta. Because the application of force and the movement of the body are in the same direction, theta is 0, cos theta is 1. So, the mass of the body is m. Because it is raised by a height h, there is some gravitational force g. So, what will be the work done? It is m into g into h. Mass of the body, gravitational force, height by which it is raised. This work done by the external force in lifting the object by a height h is stored as potential energy. V is equal to mgh. This h is said because the displacement is by a height h. Okay, so potential energy is equal to mass into gravity into displacement. Let us understand gravitational potential energy. Let us take the same example. Which example? We had a body or block of mass m which has to be raised by a height h, okay, above the ground. Work done by the external force is given by work is equal to force into displacement or force into height into cos theta. Please remember, the gravitational force is acting downwards whereas the lifting force is acting upwards. So what will happen? Theta here is 180 degree, or work done to lift this body is minus mgh. This is also stored as potential energy, but since the action is against the gravitational force, the potential energy shall be minus mgh. Okay, have a wonderful learning experience. Thank you.